so today we're going to look at a way of finding a closed form formula for a linear DDS. I'll explain all those terms in just a minute. But basically this is one of the few cases where we can actually write down a formula for xn, the nth iterate, without having to do all the work of iterating to get that far. And we're going to be using, in the process, we're going to be using the work that we did for geometric series to do so. Okay, so let's define what we mean by a linear DDS. A linear DDS has a specific form. It's xn plus 1 equals, let's say, r times xn plus b, okay, where r and n are constants. R and n are constants. So we call it linear because it looks like a line, mx plus b. And we want to actually write down what the iterations look like if we start with a particular initial value x0 and see if we can figure out a pattern. So let's start out with x0 and then x1. Well, x1 is going to be rx0 plus b. That wasn't hard. x2 is going to be r times x1 plus b. And now we're going to substitute what x1 is in terms of x0 so we can see how that goes. That's r times rx0 plus b, right? And let's multiply that out. So that's r squared x0 plus rb plus b. Let's do it again. Let's look at x3. We want to do it until we can see a pattern here. x3 is r times x2 plus b, right? And we already figured out what x2 is. This is x2. So let's plug that in for x2 and simplify. So we get r times r squared x0 plus rb plus b plus b. And multiplying that out gives r cubed x0 plus r squared b plus rb plus b. Can you guess what x4 would be? I mean, x4 is going to be r times x3 plus b. But now let's sort of be intelligent about this. We're going to take r and multiply it by this thing. This is x3. So that'll be r to the fourth, x0, plus r cubed b, plus r squared b, plus rb, plus b. And this one, no, they're all there, right? And x to the fifth, that's rx to the fourth plus b. Well, we guess that's going to be r to the fifth x0 plus r to the fourth b plus r cubed b plus r squared b plus r plus rb plus b. So I think you can see the pattern now. What we have here in the fifth term, for example, is we have r to the fifth times our initial value x0, and the other terms actually are a geometric series, right? Take a look at that. It's a geometric series. It's maybe written backwards from the way we usually write it, but the first term is b, and each other term in the series is found by multiplying by a constant multiple r, right? So this is a geometric series, and so we should be able to write down a formula for this. Let's get a new fresh sheet of paper. All right, so what we found out from our pattern was that the formula for xn if we extend our pattern, should be what? It should be r to the n times x naught, the initial value of x. And then we had that geometric series. The next term would be r to the n minus 1 times b plus r to the n minus 2 times b plus, and then that went down to, r cubed times b plus r squared times b plus r times b plus b, right? So we had this first term, which was r to the n times the initial value, and then the rest of the terms form a geometric series. And in fact, we can identify what we need to know about the geometric series. The first term equals, reading from right to left, equals b. The constant ratio, or constant multiple, is just r. And how many terms are there? Well, if you count them carefully, you see that they're n terms, right? And therefore, this term, all these terms actually add up to, since they are a geometric series, they add up to what? B times 1 minus r to the n over 1 minus r. That's from our work with that's the formula that we found from studying geometric series in general earlier. So putting all this together, we can now get the final closed form formula for xn. Again, this is for the linear DDS. It's r to the n x0 plus b times 1 minus r to the n over 1 minus r.